My name is Viktor Kirilov, and today I'll be talking about Doctest, which is a testing framework. So first about me, I'm from Bulgaria with a few years in the games and VFX industries, and for the past 2 years I've been working on personal projects. I use different compilers, and I use a lot of CMake, Git, and Valgrind, and the sanitizers. And I also think that GitHub is one of the most amazing places for software developers. It's like a social network. I'm very passionate about game development and game engines, also data-oriented design and high-performance computing, and about good software development practices. So, Doctest was inspired by the ability of other compiled languages such as D, Rust, and Nim to have tests written directly in the production code. And the mantra of the project is that tests should be considered as a form of documentation, and they should be able to reside near the code which they test. So first of all, Doctest is heavily influenced by Catch, and it models its interface to a great extent. Currently, a few big things which Catch has, Doctest is missing, like a reporter system, to XML and to other formats, and also matchers, but Doctest has some features of its own, like test suites and templated test cases. There is also this great repository by Martin, which compares Catch, Lest, and Doctest, which are three very similar frameworks. All three of them are single header and support similar features. So in this presentation, I'll first introduce you to the framework. Then I'll continue with implementation details, for example, how to automatically register code. Also, a bit about the preprocessor and warnings. I'll talk a bit about how to decompose expressions with templates and some other stuff. Then I'll finish with compile time and runtime benchmarks on how they were achieved and examples of how to integrate tests in your production code. I will not, however, be talking about how to do testing in general because that's covered in a lot of other talks. So let's get started. First of all, since it is a single header library, there are two ways we can approach it. Either everything is marked as inline and all the headers are always included, or we can separate the header in two parts, the interface part and the implementation part. The interface part is included everywhere, but the implementation part is conditionally compiled in only one source file where we have defined some identifier before including the framework. You can think of this as the library being in two files, a header and a source file, but they're in one file for easier distribution. This is a common practice for single header libraries. It's sort of a buzzword. And most of the includes and dependencies go only in the implementation part, which again goes in only one translation unit of your project. This time, this way, dependencies are contained. Here is a complete example of a program which compiles and links to an executable. First, we define some identifier which tells Doctest to implement its test runner here in this source file, and also to provide a main entry point. Then we include the framework, and then we have a function which we want to test. There is one single test case which has 4 assertions, and the first one of them will fail because we have a bug in the function. Here is what the output looks like. First, we get told which test case failed, and then which assert failed. And we even get the value of fact of 0. And at the end, there is a summary of how many tests passed and failed. So, what makes Doctest different? In 2 words, it is very light and unintrusive. It has the smallest possible footprint on compile times. You can remove everything testing related from the binary. There is no namespace pollution. All macros are or can be prefixed. Doesn't drag any headers with it. I'm talking about the interface part, not the implementation part of the framework. So if you just include it and you don't implement the test framework, you don't have included stud string or anything. It produces absolutely 0 warnings or even the most aggressive warning levels, and it's also easy to integrate with user code. The idea is that even if you include it across your entire project in each source file, that you don't notice it, not in build times, not in warnings, not in anything. It is also very reliable. It is per commit tested on Travis and Avior CI services, which are integrated with GitHub, and each time I push, all tests are built in debug and release 32 and 64-bit modes with all these compilers on Linux, OS X, and Windows. Warnings are treated as errors. I run the tests through Valgrind and through the sanitizers. Builds are built in C++98 and 11 modes, with and without exceptions, with and without RTTI, and it's statically analyzed with 5 different tools. That amounts to a lot of builds, and it took quite a lot of time to configure. So all this makes writing tests in the production code feasible, which in turn leads to lowering the barrier for writing tests. You don't have to make separate source files. You don't have to commit them to source control, to add them to the build system and include a bunch of stuff and link some stuff as well. You can just write the tests for some module at the bottom of its source file. Tests can also be viewed as up-to-date comments because the compiler enforces that everything compiles. It's never out of date. It's also easier to test internals of your APIs which are unexposed through the headers, and test-driven development becomes pretty straightforward. Even if you don't like the idea of mixing tests and production code, the framework can still be used like any other. It has a rich set of features which I'll talk about in a minute. So first, there is one core assertion macro which decomposes expressions, so you don't have to give it manually the left and right operands and tell it that it's supposed to check for equality or inequality or something like that. Also, test cases are registered automatically, unlike in the bottom case where you have to give it some unique name, some identifier, and then register it somewhere manually. So we're keeping things dry, like in don't repeat yourself. There are subcases which were directly stolen as an idea from Catch. They're a way to share setup and teardown code of tests. So suppose we want to open a database connection and then close it and do some stuff with it. If we have multiple tests that need that database connection, we can just write the opening and closing code once and write a few subcases which use the database instead of writing separate test cases and duplicating our code. There are also logging facilities. For example, in this case, if some element from the arrays don't match, we would like some context, like which element was it, so we can log the counter variable of the loop. What is special is that actually the string is not constructed unless the assertion fails. So there is lazy stringification for performance. Here, there is no allocation unless an assert fails. And the output from this would be, at the end there will be with context, the value of I is 75, if the assert fails. You can also teach the framework how to translate exceptions of user types by registering a translator function, and I'll show how that works later. And when you compare custom types in your assertions, if the assert fails, you could teach the framework how to stringify your types as well. There are also templated test cases, in which case you can instantiate a test case on a list of types. And in this case, we'll get a serialization for int, char, and my type. And in this particular case, we're testing that for each of these types, if we serialize them and then deserialize them, that the result is equal to what we started with. There are also asserts for dealing with exceptions, like checking if something throws or something doesn't throw. And there's also a utility class to help us with comparing floating point. There are also decorators. In this case, we can tell that this test case should be marked as skipped if some function returns true, or we can also mark it as we can tell Doctest to mark it as failed if it takes more than 200 milliseconds. There are other decorators as well. Just a second. So other notable features are crash handling with signals under Unix and structured exception handling under Windows. Failures can also break into the debugger, and there's a rich command line with lots of options. For example, we can list all test cases, we can filter them by name using wildcards, we can filter them by excluding them with wildcards, we can tell them the framework to abort after 10 failures, how tests should be ordered, that it shouldn't break into the debugger, and we can even ask the binary how many tests there are, and then we can do range-based execution using the executable. So Doctest still cannot execute tests in multiple threads, but you can parallelize your tests if they run slowly this way. So let's get into some details. And also the code is very simplified. This is not the actual code in the library. It's more messy in there. So at the heart of everything sits the ability to construct anonymous unique variables. For this, we're using the anonymous macro, which concatenates a literal with the result of counter. Counter is an identifier which is not standardized, but it's practically supported by all major compilers for the past 10 or something years. And each time you use it in a source file, you get a bigger integer. It always starts from 0. So in this case, when we use anonymous with anon var two times, we might get anon var 5 and anon var 6. So let's see how the automatic test registration looks like. This test case expands to the following after the preprocessor. First, we have a forward declaration of the void test function. After that, there is a global dummy integer to which we assign the result of rec test. That way, we force some code to be executed before we enter the main function of the program, because all globals are initialized. And to the call of rec test, we pass the name of the function and the relevant information like where it was written, what's the name of the test case, and we also call get from TS, which is a way to get the current test suite. I'll talk about that later. And after that follows the definition of the test case. So here I'm using static for the function and for the dummy integer because, as I said in the previous slide, counter always starts from 0 for each translation unit. So if these weren't static, I might get linker errors when I write tests in multiple source files. So when we call rec test, we need to insert this test case in some registry. But where does that test case registry live? If we just make it as a global variable where the test runner is implemented, we don't have any guarantees that it's already initialized. So in C++, there's this thing called static initialization order fiasco. And in one translation unit, you have guaranteed by the standard that all globals are initialized from top to bottom. But between separate translation units, there are no guarantees. So we need to make sure that the test case registry is initialized the first time a test case gets inserted. So for that, we're using a getter function in which it is defined as a local static variable. And then we return it by reference. So the first time this getter is called, we actually create the registry, and it lives until the program ends. So in rec test, we construct a test case, and we put it in the registry, and then we return 0 to initialize the global dummy integer, which forced rec test to be called in the first place before we enter main. So test suites. By default, all test cases are in no test suite, but we can put them inside of a block like this one. Doctest provides some default get function in a TS namespace, which returns an empty string, meaning the test case is nowhere. But when we put the test case inside of the test suite block, that after the preprocessor looks like the following. We still have the default get function from Doctest, but now we have introduced an anonymous unique namespace in which we have made the get function inside of the TS namespace, and then we close all these namespaces and reopen the unique one, the anonymous unique one again, to reuse the opening curly brace written by the user. And then when the test case macro expands and we call tsget, we actually call tsget from this unique namespace. And that's how this test case knows it is in that particular test suite. Let's talk about warnings. Doctest doesn't produce absolutely anything, even when using everything for Clang. Level 4 on Visual Studio, all is a bit too noisy. And also all on extra for GCC, and over 37 other flags which are not covered by all and extra. These are the other flags, which are pretty hard to track down, but there is a trick to see which warnings are left enabled or disabled after you have passed all, for example. And the line at the bottom is exactly that. These slides will be available later on the internet, so you can copy this line later. So the Doctest header originally produced some warnings, like some internal structure is padded. And that's not a bad warning, it's a diagnostic message. And I still wanted to silence these from the header. So each decent compiler nowadays supports a diagnostic stack to which you can push, say that you ignore something, and then pop at the end. So I've surrounded everything in my header with such pushing and popping for different compilers to silence the most problematic warnings. But what happens to warnings which are generated by the macros themselves? When the user uses the test case macro, it's not expanded in the header, it's expanded it in his source code. And it produces the following two warnings for Clang and GCC because of the global dummy integer we use to call rec test before we enter main, the unused variable for GCC, and the global constructors one for Clang. So we can't ask the user to surround his code with pragmas. What can we do? So the preprocessor works in the following way. Suppose we have a source file and a header file. The source file includes the header file. After the preprocessor, we get the following translation unit, which gets fed to the compiler. The compiler doesn't see the two files at the top. he sees the result after the preprocessor. So as we can see, the header file is included in the source file. There are no more comments. The macros are expanded, but there are still a few lines starting with a hashtag which are left. The pragma for the structure has survived because it's actually a directive for the compiler, not for the preprocessor. And also there are these weird lines with numbers and source files. Since the compiler gets only this final result after the preprocessor, he still needs to know what came from where. And in this case, we have a variable redefinition in the header file. And in order for the compiler to be able to report the proper line numbers and files for the error, exactly these weird lines are used. So we can't just embed a pragma inside of a macro, but since C++11 there is a way using the _pragma operator. It's actually been available in compilers for the past like 15 years, but now it's standardized. So here I've written a macro which expands to some for loop, which we might want to parallelize using the OpenMP extension for compilers. And when the preprocessor runs, that _pragma OMP parallel for expands to the code on the right, and we get our pragma nicely after the preprocessor. So here is how we silence the dreaded global constructors warning for Clang. We surround inside of our multi-line macro the dummy integer with such pushing to the stack, ignoring, and then popping from the stack. So, but in the case of GCC, the C++ frontend is problematic in its _pragma usage for the past like 6 years, and it doesn't work. There are quite a few issues about it. So I've been lucky that I could silence the warning by using an attribute unused to mark the dummy global integer as being, unused for anything else except for calling correcttest. So let's talk about subcases. In this case, we see that setup is printed 3 times. That means it's at the top of the test case. That means that the test case has been re-entered 3 times. And we also see that there are a bunch of nested subcases. So they resemble something like a tree. And there are 3 leaf nodes, if we can call them like that. So the execution of test cases with subcases resembles something like a DFS traversal. We go deeper and deeper until we find a leaf node, and then we pop out. And if there are any more subcases left untraversed, we re-enter the test case again. So this is very useful for sharing setup and teardown code, like opening database connections, opening files, or initializing data, or whatever. So these subcase macros expand to the following. I should also mention that they're identical to sections in catch. So, and the idea is taken from there. The subcase macro expands to the following: if statements. And in these if statements, I construct temporary objects of type subcase, which I give the information like where the subcase is defined. And then I assign this temporary object to a constant reference to extend its lifetime until we have left the entire if statement and the then block, if we enter the then block. In the constructor of the subcase class, based on the information we have given it, it uses global state from the test runner to determine if we should enter this subcase, if it has already been seen, and etc. And it sets a boolean inside of the subcase class. So when the operator bool is called on this temporary subcase object, it returns either true or false. So we either enter the if statement or we don't. I mean the then block of the if statement. Also, as we can see, subcases are lazily discovered. They're not like test cases, which are registered before we enter main. Subcases are discovered on the go, and we don't know how many subcases there are within a test case unless we enter it. So, in the first example, I showed how a complete example where Doctest brought its own main function and the implementation of the test runner. But if we're writing tests in our production code, we already have a main function. In that case, we should tell Doctest only to bring its test runner, but not the main function. And to call it, we need to make a context, then probably set some default options. Then we can parse the command line. We can even override some options. and then we call run on the context. So when we mix tests with production code, there are three scenarios we should support. We either want to run only the tests, only our program, or both. So if we have passed the exit flag to this executable, after we have called run on the context, when we ask it if we should exit, it returns true, so we shouldn't continue with our program. If we have passed the no run option, in that case, when we call run on the context, no test will be run, and when we call should exit, it will tell us false, and we continue with our program. By default, all the test cases will be run, and then we'll continue with our program. If your unit tests execute very fast, like for half a second, it's very convenient that each time you start up your program, you run also the tests. It's nice to see that green light flash. But if you write your tests in your production code, you might want to remove them out of the binary when you ship it to customers. And in that case, you can use the disable identifier globally. And then all test cases are turned into uninstantiated templates. So even in debug builds, the test cases are never instantiated and they're not present in the final binary. And that speeds up the linking time a bit. But we can take it a step further, because even if the test cases won't be instantiated, there's still a lot of code which has to be parsed. So we can also turn every assertion macro into a no-op using the void of 0, which is also used to require the semicolon which the user has written after the assert. Also, subcases just vanish, and most of the test runner is removed from the binary. Only a few stubs are left, because if you have integrated, if you have called Doctest on your own in your main function, that means you have created a context and you have called ran on it and etc. So these functions are still present as stubs. So let's talk about the expression decomposition. In this case, the assert at the top expands to the following code on the bottom. First, everything is wrapped inside of a do-while loop, which loops only once because the condition is false. I've used the void of 0, 0 trick to silence the conditional expression is constant warning for Visual Studio. Also, that way, this is a common practice to wrap multi-statement macros inside of a do-while false loop to make them a single statement, so they can be nicely used after if statements without blocks. So here, first inside of the do-while loop, we construct a result builder object, and we initialize it with like where the assert was written for information we will use later. And then inside of a try block, we'll evaluate the expression. If anything happens, we'll catch the exception, we'll translate it, as I'll show later. And then if the assert has failed, either because the assert, these things are not equal or something through, we break into the debugger right here. So how does the expression decomposition work? We construct an expression decomposer object which has the left shift operator overloaded for it. And since in C++ this operator has higher precedence over the comparison operators, actually the left operand of the comparison is swallowed by the expression decomposer left shift operator. And that operator then returns a different type, which is the type left operand, which holds the left operand. And it has overloaded operators for comparisons. And that way, then it captures the right operand, in this case B, and it does the actual comparison. And that returns a result, which is set to the result builder if nothing throws. So here's the expression decomposer class. It's just one method, which is templated to capture the left operand. And it returns, as I said, an object of a different type, of type left operand. And that left operand type is shown below. It holds a reference to the left operand, and it has the comparison operators overloaded for it, and they're also templated. So when we get the right operand as well in our comparison operator, we construct a result object. That's where we do the actual comparison, and we also call stringify on the left and right sides of the comparison. So the result object is just a boolean with the result, and also a string decomposition of the expression if anything fails. And the stringify function we called on the left and right operands just calls to string on the left and right operands. And there is a way to teach the framework how to stringify your types, but by default you get a question mark if the framework doesn't recognize your types. So if we use a function which throws an exception inside of an assert, the framework can be taught how to translate that exception. And that happens in the catch clause. And we call the exception occurred method of the result builder. So how does that work? First, we have an itranslator interface, which has a single virtual function called translate. It returns a bool, and it also returns the result of the stringification through a reference string. You could return a pair of a Boolean string. That doesn't matter. And then we have a translator class, which is templated, and it inherits from the itranslator interface. In its constructor, we accept a function pointer to a translator function for a specific type, which is the type we will be templated on. And we have also overridden the translate function. And in there, inside of a try statement, try block, we rethrow the current active exception. And then we try to catch it with the type the translator class is currently instantiated for. And if we succeed in catching it by that specific type, then we use this function pointer we have been constructed with. We translate the exception and we return true. Otherwise, we return false. So the user may register a translator like this using the rectranslator macro. And like a normal function call, a normal function definition, he says what type of exceptions it will be translating. And this expands after the preprocessor to the following. Again, like registering test cases, we first make a forward declaration of the function which the user has defined. Then we make a global dummy integer, again, to which we assign the result of rectest, rectranslator, and to it we pass the name of the translator function. And after that follows the body the user has written. So the rectranslator function is also templated, so it can capture the type this translator is written for. And inside of it, it creates a translator type as a static local variable, which means that it will be alive until the program ends. And this translator type is the one from the previous slide. And here we instantiate it for the current type of exception. And we give it this function pointer, which is the translator the user has written. And now we can pass to the test runner a pointer to this local translator object, which will be alive until the program ends. We can pass the pointer to it to the test runner because it shares a common interface, the itranslator interface. So the test runner will not know about your specific types, but it will know that it will have a list of pointers on itranslator objects. So when the exception occurred method of the result builder is called, we call the translate function, which first iterates through all registered translators and tries to translate the current exception. And if all that fails, it continues with default translation, which again rethrows the current active exception inside of a try block and tries to catch it as a stud exception, as a stud string, or a const char. And if all these fail, it returns the default message unknown exception. So let's talk about compile times. They're like the Achilles heel of C++. This is a benchmark comparing how much it costs when you include the doctest header and the catch header in an empty, totally empty source file. Doctest is always around 20 milliseconds, where catch is almost half a second. The reason for that is that Doctest doesn't include absolutely anything in its forward declaration part, the interface part. So after the preprocessor, it's only 1,200 lines of code, specifically for Visual Studio. And catch is around 40,000 lines of code. This is because I said that before. Here, I don't want to bash catch because it's an amazing project, and actually Doctest wouldn't exist without it. I've been piggybacking on a lot of the features and ideas from catch, and also catch is still much in development, and they're incorporating very many of the ideas I introduced in Doctest. Also, boost test also has a single header form, but it is madness. I mean, it's like 10 or 20 times slower to compile than catch. I mean, nobody uses it, I think, in its single header form. So I need some types from the stud namespace in my interface, but I don't want to include anything. For example, for stud.stream, there is the iOS FWD header, but in its case, I mean, in the case for Visual Studio, when I include that header, after the preprocessor, without comments and macros, I'm left with 9,000 lines of code. And that's like 8 times more than my interface entirely. So I don't want to include that header. So I just forward declared stud.stream myself. That's against the standard, but it practically works everywhere and on all those compilers I'm testing, like from GCC 4.4 to 7, all Clanks and all Visual Studios. And even if something goes wrong, there is a configure option to actually use this header, which for other compilers is actually much smaller. Like for Clank, it's 500 lines of code, not 9,000. And also there are other libraries which forward declare stuff from the stud namespace. For example, BoostDI does the same. It includes absolutely nothing. So let's talk about the cost when you include the header and you also implement the framework. Again, Doctest is faster but to compile than catch, but I don't consider this important because this is done in only one source file. You instantiate the test runner and you compile it only once, and in all of the other source files you have in your project, you use the interface, not the test. You don't compile the test runner everywhere. And also, as features are added to Doctest, it will also get slower in its test runner. That's inevitable. And also, something else we can see is that compilers differ very much between each other, and also the bug versus release is wildly different in compile times, and that's quite interesting. So let's talk about the compile time of the assert, because how much it costs to just include the header is only one part of the story. Doctest supports the normal expression decomposing form of its asserts, which you don't have to explicitly say the left and right operands with a comma. But for performance freaks, there are also other macros. For example, there are binary ones, which skip the template machinery to decompose the expression. You give it explicitly what's on the left and on the right. There are also the fast binary ones, which in addition to not having to decompose expressions, they also don't evaluate the comparison inside of a try block. And if we define the super fast asserts identifier, then they become even faster, and I'll show what that means a bit later. Catch has the expression decomposing asserts, and it also has a fast compile option, which also removes some of the functionality of the asserts, like in my case. It removes the try blocks, and it's also a bit like the super fast asserts, which I'll talk about later. So in the benchmarks I'm about to show, I compiled 500 test cases with 100 asserts in each of them, and that amounts to a total of 50,000 asserts. So here are the results. Oddly enough, GCC is quite slow in release, both on Windows and on Linux. There are very much differences between compilers. The 2 red lines are for the 2 forms of the asserts for catch, and the other 4 bars, which are the blue ones and the green and brown one, are for Doctest. And as we can see, you can get crazy performance with the fastest form of the asserts for Doctest. I mean, you can get 50,000 asserts to compile for like less than 10 seconds. So this is what the normal assert, which decomposes expressions, looked like in the first version of the library. And it was terrible code bloat. Then my asserts were a lot slower to compile than those of catch. And that's because a lot of stuff ended up generated after the macro, which didn't have to be there. And in Doctest 1.1, the same assert looks like the snippet at the top, just the bare minimum. The do-while loop, the result builder object, the try-catch statements, and an if statement to check if we should break into the debugger exactly there. The fast binary asserts, again, are even less code, and that's why they compile faster. And they're, again, inside of a do-while loop, because we have 2 things we have to do. We have to call the assert function, and we have to do an if statement if we should break into the debugger. And when we define the super fast asserts identifier, those same fast binary asserts become a single function call. And the only downside is that when the assert fails, we don't break into the debugger at this exact point in the source code, but one level deeper in the call stack, which means in the fast binary assert function. And we just have to go one level up in the code stack to see where we are actually in the source code. And in my opinion, that's a pretty good price to pay for the compile times you get if an assert expands to a single function call. So very much depending on the compiler and the configuration, those 50,000 asserts, the normal ones which decompose expressions, may compile for 20 or more than 200 seconds, which is roughly around 50% faster than catch. And the fast versions of Doctest, the fastest, maximum possibly fastest ones, compile for between 3 and 16 seconds, again depending on the compiler. And that's pretty good for 50,000 asserts. And to achieve these results, a lot of functions were marked as explicitly not to be inlined. Many constructors, destructors, the fast binary assert function itself, yeah, many things were marked no inline. But this doesn't have a big impact on runtime performance, which is the next topic. And these benchmarks were done 2 weeks ago with almost the latest versions of the frameworks. And you can also check out this link, how they were done. So here we see a loop which loops 10 million times, and it compares an integer to itself. Pretty stupid, but it can't get optimized away because there might be side effects. And it's not optimized away. So one interesting thing to see is that Visual Studio in debug takes a lot of time to compile. But on all other cases, both frameworks are pretty fast. And both frameworks have made significant progress in their runtime performance in the last 5 to 6 months. Actually, first Catch started doing that, and I saw that they're doing that, and I got the idea to do the same, because some users were reporting that their unit tests ran for like 10 minutes, which is crazy. I mean, I don't know how many asserts they have, but maybe it's a problem for them. So, the latest version of Doctest is more than 30 times faster than its previous version. But here I'm talking only about the common case where no assert fails. And that's the common case, right? If you have 10 million thousand asserts and only 5,000 of them fail, you should optimize for the ones which don't fail. The biggest gains I got were by not constructing strings if the asserts don't fail. So I reordered a bit my logic around the asserts. The second biggest thing for gains was, since I don't include stud string in the interface of Doctest, but I still needed some string class, and I implemented my own. And for it, I implemented the small string optimization based on the ideas in Nicholas Ormrod's Strange Details of Stud String at Facebook talk from last year's CppCon. It's a great talk, very insightful. I highly recommend it. So these two were practically the reasons Doctest became 30 times faster compared to its older versions. Move semantics don't play any role in the common case when nothing fails, because there are no allocations, and move semantics are helpful when there are deep copies, and when nothing is allocated, you don't have deep copies because everything is on the stack. And one other minor performance gain was by not using any local statics on the hot path when asserts don't fail. So if you have been convinced that it's practical to include this framework in your production code and just mix production code and tests, you have several options. If you're writing an end product for users, not for developers, you can just mix the code and tests, and then when you finally make the final build, you can define the disable identifier, and there are no tests in the binary anymore. And you can also not remove the tests, but disable them by default by setting the no-run option to true. And that way the user will still have the tests in his binary. And for example, if there is a problem like something you can't reproduce it on your side, but only the user is experiencing it, you might ship him a binary with tests, and he can run them on his platform to see if anything fails there. And also, this won't impact any runtime performance, dragging these tests along with the binary, because they're code. Yeah. Especially if you use profile guided optimizations, they won't be any near the hot path of your application. So if you're developing software which is not for end customers, but for developers, and if you're writing header-only libraries, you might put your tests at the bottom of your library, surrounded by some if-def you have written. And so your users might just include the header and use the functionality, or they might define that identifier before including it, so they get the test as well. And they can even use a version of Doctest of their own if they have included it before your header. It's also a good idea when you're writing a library for other developers with tests in it to either prefix them in their names with the name of your library, or put them in a test suite with the name of your library, so your users can filter easily the tests for a particular third party. In the case of compiled binaries, let's talk about firstly about shared objects and DLLs. You have to instantiate and implement test runner in each DLL or executable. But that makes integrating all the tests hard, because you have a bunch of test runners and a bunch of test registries, and you can't easily integrate them. Yeah, you can't, unless you use this identifier globally. Using it, you can define the test runner and implement it in only a single binary. It can export all the symbols, and all other binaries can link to it, so only a single test registry lives in your application. So that's about shared objects and DLLs. In the case of static libraries, there are issues with self-registering test cases. And these issues are common to all testing libraries and benchmarking frameworks which register code automatically. There are ways to combat that, and you can read more about it in the FAQ of the documentation. Here is how I use Doctest. I have a proxy header, which includes the actual header of the framework. I first remove the short versions of the macros, and also then say that I want the maximum, possibly fastest versions of the fast binary asserts. And then I define the asserts in the way I would like to use them. And then I just include this proxy header and write my tests along my production code. Most of the effort in making the framework went into, firstly, familiarizing myself into testing and other testing frameworks. Also, not making sure that nothing is dragged in the public interface of the library, that no header is included there. Also, the 300 plus different CI builds, they might be even 400, they took like literally at least 3 or 4 weeks of compacted time and just waiting for 3 hours to see if something fails, or if GCC 4.7 tells you that something got inlined, which is not a warning, it's a diagnostic, but it's only for GCC 4.7, etc. Also, the strict overflow on level 5 was very fun because it got triggered only on some compiler versions, only in release builds, when something got inlined, and inside of it I have some problematic arithmetic, and in the report it says that it's on line 0. I mean, I don't know what got inlined, and I don't know on which line, So that was fun to track down, but I'm clean from strict overflow on level 5. I'm not sure if anyone uses that in real production, but yeah, Doctest is clean. I also found my first unique bug in GCC in its integration of the sanitizers, and there were also quite a bit interesting toolchain problems. Even now I have a few builds marked as allowed failures on Travis because the sanitizers for GCC 4.8 and under OS X from Homebrew, they don't work. So what lies ahead? There should be a reporter system, because currently Doctest only reports in the console what passed and what failed, and returns either 1 or 0 as an exit code. There should be XUnit, JUnit, etc. style of XML output. It should be cool if tests can execute in separate processes, especially under Linux. That's not just to combat crashes, but also to isolate tests if they use global state. Death tests, which is an idea taken from Google Test. Generators for data-driven testing, matchers, more command line options. A big one is integration into IDEs, because currently Doctest doesn't have adapters for Visual Studio or Xcode or CLine or anything like that. And another big feature which is coming sometime is thread-safe assertions, where you could have not having multiple test cases running in parallel, but if you instantiate a number of threads within a single test case, and if you want to call assertions from the multiple threads, that should be possible in the future. And there is a huge roadmap, like with more than 200 ideas, or no, 100 ideas of what to add to the framework. But these are the biggest ones. So the initial concept got into my head like 3 years ago, and when I quit my job 2 years ago, I started the accelerated development of the framework. Those are the 3 major versions, where the first one was with a focus on the compile time of the header, then the compile time of the asserts, and the last one was with features and runtime performances. It's a bit late to the party because all the major testing frameworks have already been written, and lots of projects are using them. But I believe that these results wouldn't have been possible without starting from scratch, especially the lightness of the header. I mean, not including anything in the public part of the header is, you have to do that from the ground up. And a modest goal for Doctest is to make it the de facto standard for unit testing in C++, almost like a language feature. The idea is that you can just include it and not notice it, and write tests if you want to, because it's so light and you don't see it. So this was it. You can check out the slides, the project, my personal site, GitHub, Twitter, and etc. Thank you. And if there are any questions, I'll be very happy to receive them. And so, any questions? And yeah, I don't know where the mic is.
Okay, first of all, thank you for the demonstration. It's not working, right? Okay, I was using Catch. It seems that you did kill Catch right now.
What?
Yeah, I was using Catch on my project. It seems that you already match a lot of the features from Catch.
Yeah, most of them, but there are a few important ones which are lacking. But you know, it depends. Yeah.
Okay, so are you working with them to build your roadmap?
No, but I think we should be. Because I've been piggybacking on some of their features, like the signal handling for crashes. I took it from them directly.
Okay, and about your roadmap, how do you prioritize the features? Because I'm very, very interesting. So how can we impact the way the roadmap is going on?
So the question is how users could impact what gets implemented first. Well, issues, I don't know. Just submit an issue on GitHub or write to me on email or in Gitter, let's discuss it. And I think I'll prioritize now the bigger features, like integration in IDEs and trying to make thread-safe assertions, but that will require C++11, and it will be conditional. But okay. I'm open to suggestions on how to discuss what's next.
Okay. Did you plan also to match some mocking framework?
The question is if I plan anything related to mocking, and yes, but I first should familiarize myself with mocking in general, because in my previous jobs we didn't do any testing and mocking, and I'm catching up on many of these areas. But it is planned. Also, property-based testing is interesting. I think it's related to data-driven testing, okay. And yeah.
Thank you very much.
Is it possible to register tests not in static initialization, but after main is executed?
Yes, but it's not exposed. But it is possible. Mm-hmm. The question was if you could not, if we could skip the automatic registration of tests, right? Mm-hmm. Yeah, it can be, but it's not yet. It doesn't have a public API yet.
And second question, do you have any special considerations for storing tests in libraries that are dynamically loaded?
Yeah, well, the question is if tests can be stored in dynamically loaded libraries. Well, yes, if you use that identifier I showed, I'll show it now. This identifier, when you build all of your binaries and separate shared objects, only one of the binaries will export the test runner, and all of the rest of the binaries will have to link to it to share the same test runner. Is this your question?
So, I mean, all libraries are loaded like with DL open or load library.
Yeah, I'm even using that. I mean, in my toy game engine, I have plugins which are dynamically loaded, and they can have tests in them, and it works.
Thank you.
Yeah.
Hi, I was really curious about your use of forward declares and how you're avoiding header includes in general.
Yep.
I was wondering if you could elaborate a little more on that. You kind of alluded to it in one of your first source code slides, but it was just...
So the question is if about to elaborate on the forward declaration stuff from the stud namespace or in general?
Well, in general, because you would also house some from your own source code, right?
Yeah, so in the interface of the library, there are a bunch of macros. I mean, 2/3 of it is macros, like 3,000 lines of code maybe. And the rest is a few forward declarations. The translator stuffs, which are templates, they have to be in the header as well. And there are a few things from the standard which are forward declared. So far, it's only stud ostream and the null putter type. Does this answer your question?
Yeah.
Okay. Anything else? Well, I guess we should close the session. Thank you very much.